This problem gives us a spherically symmetric charge distribution where the density of charge decreases as we move outwards towards capital R, the radius of the sphere. Part A asks us to show that the total charge contained in the sphere equals capital Q. We can do this by setting the charge Q as a function of R equal to the charge density ρ integrated over the volume of the sphere. The volume element dV is equal to the surface area of a sphere of radius r, that's 4 pi little r squared, times the differential dr. So here I'll draw a second sphere with a very slightly larger radius, and the differential volume dV I'll draw in blue here. So this element is the surface area 4 pi r squared times dr. When we substitute in the expression for ρ naught that we're given in the problem statement, we end up with this integral that we need to evaluate from 0 to some arbitrary point little r. And we're integrating over the dummy variable r prime. Simplifying this integral gives us this expression, which we can easily integrate to find the charge inside a radius little r. We can simplify this expression a bit by factoring out an r cubed, obtaining this final result, which I'm going to write up here at the top because we'll need it a few times as we go through this solution. Now to solve part A, showing that the entire sphere contains charge capital Q, we just need to substitute little r equals capital R into this expression. That's shown here, where we can notice that this term in parentheses now equals 1, and the r cubes cancel, giving us the result that we were asked to show. Part B asks us to find the electric field inside and outside the sphere. Let me erase all of this so that we have room to do that. Let's first look at the region outside the charge distribution, where little r is greater than or equal to capital R. Gauss's law tells us that the integral of E dot dA over a closed surface equals the charge enclosed by that surface divided by epsilon naught. The Gaussian surface we choose is a sphere centered on the charge distribution, so that E dot dA equals E times dA. The electric field is constant on that Gaussian surface, so we end up with this familiar result. The charge enclosed by that Gaussian surface is the entire charge capital Q that we found in part A. So the electric field is just Q over 4 pi epsilon naught r squared in the r hat direction. I'll write that result over here, valid outside the charge distribution where little r is greater than or equal to capital R. Now we need to change and look inside the charge distribution where little r is less than capital R. The only thing that changes in our solution is that the Gaussian surface no longer contains the entire charge capital Q. It only contains charge little q as a function of r. So when we make that replacement, substituting in our expression that we put at the top right, we find the electric field is given by this expression. So inside the charge distribution, we have this electric field, which I'll record over on the right so that we can use it later. Part C asks us to plot this electric field as a function of r. Let me erase so that we have room to do that. I've shown the plot here, where the horizontal axis is the radial distance r, and the vertical axis is the magnitude of the electric field E. There are two curves here, matching up at the radius capital R. The red curve corresponds to this equation outside the charge distribution, and the blue curve corresponds to this equation, which I'll box in blue, inside the charge distribution. These two curves meet where the electric field magnitude has the value Q over 4 pi epsilon naught capital R squared, which for simplicity I'll call E sub capital R. We're now asked to find the maximum value of the electric field. That's the value of the electric field right here, where the slope of the electric field is 0. We'll find it in the usual way by setting the derivative of the blue function equal to 0, finding the position r where that occurs. If we calculate the derivative of the blue function with respect to r, we get this expression after employing the product rule. If it's to equal 0, this term in brackets must equal 0. A bit of rearranging shows us that requires 6 times little r over capital R equals 4, so that the maximum field occurs where little r equals 2/3 times the radius of the sphere. This is where the maximum occurs. To find the maximum electric field, we substitute that into the expression boxed in blue over on the right. So let me one more time erase this, so we'll have room to do that. Substituting little r equals 2/3 capital R into the blue expression gives us this result, which we can simplify by canceling terms in the numerator and denominator, seeing that this term in parentheses just equals 2, canceling this r with one of those, to notice that this in front equals E sub r. And now combining these 2's and this 3, we see that the maximum electric field is 4/3 the value E sub r. 4/3 the value where those two curves meet. Substituting in our expression for E sub r finally gives us this result, the maximum value of the electric field.